All right, let's go on to example 2. We're going to use exactly the same trick. So we're going to translate the interval from 0 to 2 pi into the circle. So using z equals e to the I theta, and dz over iz is d theta. And so cosine is 1/2 z plus 1 over z, and sine theta is 1 over 2i times z minus 1 over z. And we're going to use it on the integral I is equal to the integral from 0 to pi of d theta over 2 minus cos theta. Now, as it stands, we can't use this trick because we're only integrating over half of the circle. And the residue theorem doesn't work unless we enclose the residues. But in this particular case, this integrand is symmetric on the integrals 0 to pi and pi to 2 pi. So when you plot it, it's exactly the same. And the reason is cosine is symmetric about pi. So if we integrated the whole way, we'd actually double the value of the integral. So this integral, I, is 1/2 the integral theta equals 0 to 2 pi of d theta over 2 minus cos theta. Now we could have chosen to go from minus pi to pi, and the same symmetry would apply. That would be going around the whole circle all at once. However we get there, 2i is this integral around the whole circle. And we can transform this real integral into this integral around the complex contour mod z equals 1. And d theta becomes dz over iz. And the 2 remains the 2. And the cosine theta becomes 1/2 z plus 1 over z. And this is very clearly a rational function. We just multiply it all out there. And when you take the I out front and do all this 2 bringing it up top, we wind up with minus 2 over I, integral around mod z equals 1 of dz over z squared minus 4z plus 1. Well, we know how to factor z squared minus 4z plus 1. That's just a quadratic. We use a quadratic formula. We get z1 is 2 minus root 3, and z2 is 2 plus root 3, and this factors as z minus z1 times z minus z2. z2 is 2 plus root 3, which is way over here someplace, just well outside the circle. So we don't really need to worry about a residue at z2. But z1, well, z1 is 2 minus root 3, and of course you can use a calculator and work out that it's a little bit more than 0.2, and less than 0.3, so you know that it's between 0 and 1. But if you don't have a calculator handy, you can say, you can start from 1 is less than root 3, so adding 1 to both sides gives us 2 is less than 1 plus root 3, and you subtract root 3 from both sides, so you get 2 minus root 3 is less than 1. Yay. And you can start from 3 is less than 4, take the square root, so root 3 is less than 2, and then you can subtract root 3 from both sides and say 0 is less than 2 minus root 3. So 0 is less than 2 minus root 3 is less than 1. So that means that the pole that we care about is somewhere there. And the other one is way off there someplace. We don't really care about that. So we only have to compute one residue to do this integral. The residue of 1 over z minus z1 times z minus z2 at z equals z1. Just the cover-up method, you get 1 over z1 minus z2. And z1 minus z2, this cancels with this. This minus root 3 gives us minus 2 root 3. So 1 over minus 2 root 3 is minus 1 over 2 root 3. So this integral, which is 2i, is going to be minus 2 over I times 2 pi I times the sum of the residues inside the circle. And there's only one of them. That's minus 1 over 2 root 3. So we cancel all the factors of 2. We cancel the I. We cancel the minuses. And we get 2 pi over root 3 for 2i. Therefore, I is pi over square root of 3. Again, this is an integral that we've done completely without finding an antiderivative. We didn't even take a derivative this time. We just evaluated a residue. So all we had to do this integral was compute one partial fraction decomposition and one coefficient, and that's it. And the rest is arithmetic. Whereas if you want to do this integral by real variable methods, I only know one real method to do it. And that's to put a variable, let's call it u, equal to tan theta over 2. And you turn it into a rational function, again do partial fractions, but then you integrate each term, you get logarithms, and then you substitute the upper and lower limits on. You get the same answer, but it's, in my view, more complicated and a little bit more fraught with error. That said, it's a little bit more powerful because you can do an indefinite integral. Here we can't do an indefinite integral on this one because we can't stop short of 2 pi. We have to do the complete cycle. We could do 2 cycles and count the residues twice, but we can't go part way without symmetry. So on the one hand, this is a simpler technique. On the other hand, it's suitable only for definite integrals, such as this one. Thank you.